Geeks for Geeks question for 12th May, meeting rooms 3. So this is the third part of this question actually. You can also do 1 and 2. It's not actually that much related, so fine. The problem here is that we are given 2 rooms and we are given a set of meetings. We have to organize these meetings in these 2 rooms only with as little or maybe no delay in the meetings, in the meeting time. This 0 is representing the start time of the meeting and 6 is representing the end time of the meeting. So there are 2 rules actually in order to assign the meeting to a particular room. If there are multiple free rooms, we have to assign the smallest room index. For example, suppose room number 0, here n is 2, right? So there are 2 rooms, room 0 and room 1. So if both the rooms are free, then we have to assign room 0. We have to prioritize the room with lesser index. And otherwise, suppose both are filled, there is a meeting going on in room 0 as well as in room 1. So otherwise, delay the meeting as less as possible. So suppose the meeting in the room 0 is going to get finished at time 4 and the meeting in the room 1 is going to get finished at time 2, right? And the current meeting, the third meeting that we are supposed to assign, is starting at time 1. So we should not here care about the smallest index. We have to check which room leads to as less delay as possible, and that is room 1, because it is going to get the delay of only 1, right? Because room 1 meeting will finish at time 2 and currently we are at time 1, so only 1 unit of delay. So that is how the rules work. What we are going to use here, okay, first of all, what are we going to return? What is our objective here? What do we return as our answer? We return the room that has the maximum number of meetings organized in it. And suppose if there are multiple rooms with same number of meetings organized, we return the smallest one. For example, room 0 had 3 meetings organized in it, room 1 also have 3 meetings organized in it, so we have to return 0 because it is smaller index. So the data structure we use is 2 priority queues in order to apply the logic, and a vector. Vector is nothing but to store the count of how many meetings were organized in which rooms, right? So it is just to calculate the answer. Our logic has to be implemented with these 2 priority queues. So let us see the approach. The first thing that we are going to do is sort the meetings by the start time. Here in the first example, they are already given by sorted start time, but it is not necessary, so we have to manually sort them. Next is we are going to maintain 2 queues. One priority queue is called, let's say, initial, and second priority called, let's name it PQ. Okay, initial queue is going to store how many free rooms are available, and PQ is going to store the rooms in which the meetings are going on right now. Okay, so we have to traverse each meeting and we have to apply these 4 steps and our answer will be calculated. So first step is to make sure that our initial queue is updated. So how are we going to store, what are we going to store in initial as well as in PQ? So their format is a little different. In the initial queue, suppose we have 2 rooms here, 0 and 1. So we are going to store 0, 0, 1, 1 in the initial queue. Why? Because in the initial queue, there is no end time, right? All we care about the room index. So, and also these priority queues are mean heaps. So the room index with the minimum value has to be prioritized in our question because it is given here that assign the smallest room number. So that is why we are storing it like this. For example, here the initial queue is we are storing 0, 0 and 1, 1, because if there are multiple rooms available, suppose there are two rooms available, 0 and 1. So we have to fetch 0, 0, not 1, 1, and the mean heap will by default apply this logic. So it will be helpful to store the data in the initial queue like this. But in the PQ, the second queue that is holding the current meetings, we will store the data as the first value will be the end time of the meeting and the second value would be the room index. That is how we are going to store data in the PQ. Okay, so let's go back to the algorithm. Keep the initial queue updated. The first step is that we have to make sure that if any meetings got ended, we have to update our initial queue. Next, if the initial queue is not empty, if there are free rooms available, we assign the one with the smallest index. How do we get the smallest index? Because of this logic. We are storing it as 0, 0, 1, 1, 2, 2. That is why the 0, 0 will be always on top. So the smallest index will always be on top. Next is otherwise we delay the meeting as little as possible. Suppose the initial queue is not at all empty, so we have to move to our PQ. We will get the topmost element from the PQ. So how will the topmost selected in the PQ? PQ is also mean heap, so minimum value will be popped out first. So the meeting whose end time is the smallest will be popped out first. That is how we are going to get the first, right, the first meeting that is going to end. And we will assign that meeting, we will assign the index, the room index of that meeting to our new meeting. Suppose, for example, the new meeting is starting at 4 and it is finishing at 6. Okay, now the current meeting, that is there is no available, there is nothing in the initial queue. In the PQ, there is a meeting that is finishing at 5 and its index can be anything, let's say n. Okay, we don't care about the index actually when it is PQ. We have to assign the one that finishes, as we have to minimize the delay basically. So now what is the delay here? Delay here would be the end time. Delay here would be the end time of the meeting that is in PQ, that is 5, minus the start time of the current meeting, that is 4. The delay here is 1. So we have to increment the end time of the new meeting, that is 4 6. We have to increment the end time by this delay, right? Because if it is starting by 1 unit late, it is starting at 5 instead of 4, of course it is going to finish at 7 instead of 6, right? So that we will take care when we insert the meeting in the PQ. Okay, then we will keep updating the answer. How will we keep updating the answer? We are going to increment the count of, in the vector we are going to increment the count of n by 1, right? And basically we are going to keep the track of two variables, maximum and answer. Maximum is going to store what is the maximum number of meeting organized in a particular room, and answer is going to store the index of the room, right? That is so simple. That is just if condition. So let's perform the dry run here. Initially the queue is like this, 0 0, both the rooms are free. So the first this arrived is 0 6. Initial is not empty, right? So we popped out 0 0 and we replaced it with the end time and the room index, and then we inserted it in the PQ. So the maximum number of meeting organized here is 1 in a particular room, that is 0. So we keep updating the maximum and answer. Now when the initial value is, when we reach I is equals to 1, here 0 0 will be popped out from the initial because it is no longer free. It is going to end at time 6. So whenever the start time, here the start time reaches time 6, only then this 6 0, that is 0 0, will come back to the initial queue. Till then it is going to stay in the PQ. Okay, so in the second iteration, when I is equals to 1, all we have in the initial queue is room 1. So room 1 is available. As long as the room is available, we are always going to take the value from initial because we don't want to delay unnecessarily, right? So 1 1 is replaced with 3 1. Why? Because the end time of this meeting is 3 and the room that we assign is 1. Okay, so the PQ is holding these two values right now. So what about the count vector? Count of 0 is 1, count of 1 is also 1, but the answer here is 0. Why? Because if the count of two rooms is same, we have to prioritize the smaller index in our answer. That is why. Next is I is equals to 2. Now here you will see the initial was empty. Here we popped out 0 0, here we popped out 1 1, but now 1 1 is back. Why? Because as you can see here, the start time is 3 and the meeting, the PQ, the meeting that is going on in the room 1 is being finished at time 3, right? So that meeting, that room becomes free now. So this is the first step. Keep the initial queue updated. We have to make sure, the first thing that we make sure is that our initial queue is holding all the free rooms, right? So that is why a room is free. So we assign it with the next meeting. Next is 3 7. So here we assign the end time of the meeting, the room index. So here is the updated PQ. Now the number of meetings organized in room 1 becomes 2, and that is why our answer becomes 1. The number of meetings organized in room 0 is only 1 and here it is 2. That's why. Then I is equals to 3. Now see, this is 4. Any meeting is being finished before 4? No. So basically that means that the initial queue is empty. There are no free rooms. So we must delay the meeting. But how much do we delay? We delay as less as possible. So which meeting is going to get finished first? 6 or 7? This is n time, 6, right? So we have to delay by 2 units. So how do we calculate this 2 units? So we basically do 6, this 6 one, right, minus this start time 4. So that is 2 unit of delay. So this 4 to 8 meeting will become 6 to 10. Okay, so we have to replace this 6 to 60 with 10-0, right? 6 was the end time, this meeting got finished, and this 8-0 became 10-0 because it got delayed by 2 units. So this is our updated PQ. Now the number of meetings organized in both rooms become 2, and we have to again prioritize the index, smaller index. That is why our answer becomes 0. Next, at I is equals to 4, initial is again 0. Why? Because you can see the start time here is 6, and both meetings here, this meeting will finish at 7, this meeting will finish at 10. So we have to delay, but we have to delay as less as possible. So we are going to delay 7. We are going to delay only 1 unit. It is 7 minus 6, 1 unit. So 6-8 will become 7-9. So then we are going to update our PQ again. This 7-1 will be replaced with 9-1, the end time of the new meeting, and the room index 1. So this is our priority queue at the end, and all the meetings are going to get finished by time 10. And at the end, the number of meetings organized in room 0 are 2, and the number of meetings organized in room 1 are 3, and hence we are going to return our answer 1, the room number with the maximum number of meetings organized in it. Now the complexity of this approach is m log n plus m log n. Why m log m? Here the m basically refers to the size of meetings. So m log n is for sorting all the meetings basically, and m log n is for the priority queue, sorting that happens inside the priority queue. At max, only n instances will be in the priority queue, even if you combine both of the priority queues, right? Because there cannot be two, there cannot be 2 entries of one room in priority queue. For example, room number 1 is free, then there is then it is in the initial queue, right? If it is busy, it is in the PQ. It cannot be in both at the same time. So at a time, we're only sorting at max n values. So this is the complexity of sorting in the priority queue. This is the complexity of sorting in the initial sorting that we are doing in the first step. And the space complexity is of course O of n. As I said, there can be at max n entries in the priority queues. And also the vector that we are using, it also holding n values only. So here is the code, right? I'm not going to write this line by line, but it is exactly same. Let me explain. First step that we have sorted this, right? This is our count vector that we are holding. This is our maximum and answer variables. These are 2 priority queues, as I said, initial queue and the PQ. Then we initialize the initial queue with II, let's say 0, 0, 1, 1, 2, 2, these values, right? Then we are traversing each meetings. S represents the start time, E represents the end time of the meeting. And what we are doing here, we are updating our initial queue. So as long as the priority queue means, as long as there are meetings in the PQ, if there are meetings, only then they get finished, right? Only then we have to check whether any meeting is being completed at this moment or not. And PQ.top.first, that means this value, this end time 6, 7, these are PQ.top.first. If they are less than or is equals to S, less than or is equals to start time. For example, here we did, here the PQ.top.first was 3, and these the start time was also 3. So if it is less than or is equals to 3, we remove it from the PQ because this meeting has ended, and we update the initial queue. That is what we're doing. This is the step 4 of our algorithm. Next, that we assign the room. If the initial is not empty, we basically assign it. So empty is equals to initial.top.second. This is the what index? Room index. We can also do first. They are the same values, but it is good because in PQ we are storing it second. So it's good practice to do the second only. Initial.pop, we are removing the room from the free queue, and we are adding it to the busy meeting queue, and we are also incrementing the count. So otherwise we are going to apply this logic that we will count the delay units, and then we will also, this E minus S is a delay unit, and this is the end time. So we are going to get new end time, and similarly we are going to push it in the PQ, right? And this is how we update. If the count of empty, that is the empty refers to basically the index of our room, right? So if the count is greater than maximum, or if it is even same, but the value, the index is smaller than our current answer, then we are going to update our maximum and answer, and in the end we return our answer. So it is returning completely fine. All right, I will upload this in the GitHub. Link will be in the description. Thank you.